this is a very typical PE type of problem, NEC PE type of problem. So you see this a lot, and you're most likely going to see this in the PE exam as well. It's a very typical voltage drop type of question. So essentially here we are given a main distribution panel of 480 volt. We have 500 kcmil DHWN copper phase conductors, 250 feet long. And we have another panel here getting served by a balanced load of 400 amp at 0.8 lagging power factor. So the question here is asking for the voltage at the load here. So just visualizing this and going back to your elementary basics, I guess, of KVL, you have a voltage here and another voltage here. So to get the voltage here at this panel, all you need is the voltage drop across the conductors. So you get your source voltage minus a voltage drop here, and you will be able to find the voltage across this panel here. So let's set up the equation. So essentially we need to find the voltage drop here, and in order to do that we will need table 9 of the NEC code to be able to get the impedance of the conductors, because V equals IR, right? So we do not know the value of the impedance, so this is what we need: R plus JX of the impedance. This will be the impedance, and we calculate the voltage by multiplying by the current and subtract 480 volt, and we'll be able to get this. So very simple if you actually visualize it, so it's not confusing. Let's not confuse ourselves here. So let's go to table 9. So table 9, we have 500 kc mil. It's right here, 500, right? So steel conduit, if you read the problem, so our reactance for all wired steel conduit will be equal to 0.048. So let's write that down. Now be really careful here, because it's R plus J. You can don't start with thinking that your reactance is your R, because some people kind of get that mixed up a little bit, just normal mistakes, right? So that's why I write it down, making sure that the first value that I write is the reactance instead of the actual resistance or value. And you can solve this in 2 ways, and I'm going to solve it both ways so you can see which one you use. Both of them are correct. I like to use this first method, but it's up to you. A lot of books solve it using the Z method, if you will, but we'll see how it goes. So J048, going back to the table, 500 kcmil, a steel conduit, copper is right here. So this would be 0.029, and we're using this value here because it's in feet, right? We are given the distance of 250 feet. So if the values were given in kilometers, we would be using the upper value, but because all the units are in feet, that's why we're using the second value for our resistance here. So where was I? Over here, 0.029 steel conduit. Let's verify, making sure, right, that we got the correct value. So make sure you get it and don't mix it up, because otherwise you will be you'll have inverse values of what you really need. So a lot of people start, I guess I will talk about the other method after I'm done with this. So this is your impedance, right? But this is across 1,000 feet per 1,000 feet, right? And we have a 250 feet distance of conductors. So essentially we have 480 volt. You can set it up this way: 480 volt minus the voltage drop across here, V is equal to IR, right? So this is our impedance, and this is the current here, but we have a 0.8 power factor. So our voltage across these conductors would be I, lagging, so the angle is negative, I, and then R would be our impedance here, already calculated to be plus J0048 per 1,000 feet, 250 times 250. Now be really careful here, because we have a we're using the line to line voltage, and this voltage that we're calculating here is the what do you call it, the line to neutral voltage. So you can either multiply this whole thing by square root of 3, the voltage drop here, you can multiply that by square root of 3, or you can divide this by square root of 3, the 480 volts, so that you're just only dealing with line to neutral, and then afterwards multiply by square root of 3. Either way you do it, it's going to be the same thing. But I just want you to recognize that this voltage across the conductors here is a line to neutral voltage, and here we're using the line to line voltage, so we want to make sure that we are subtracting oranges and oranges, right? So here, this is a line to neutral voltage, the middle part here. This is a line to line voltage. You cannot subtract the two. So either this one will have to be a line to neutral voltage, or this one will have to be a line to line voltage. Either way you do it is the same thing. So let's go ahead and multiply this by square root of 3 to bring it back to a line to line voltage. So this is pretty much it. You set it up this way and plug it into your calculator, and the answer would be in volt. So V is equal to 471. So you can do it this way. I like this method because I can clearly see that I have a source voltage and I'm getting a voltage drop here. What's my voltage drop? Subtract it, and then get this voltage across here. But there are some methods, another way to do it. Let's erase this thing. I like this method. I mean, yeah, I mean, this is what I used during the exam as well. I guess I don't have to delete that. Let's not delete that. Let's keep it. All right, let me use a different color though. All right, so the other method would be to use your effective Z. So basically using the power factor that's given. So you have Z is equal to, remember, R cosine of theta plus X sine of theta. So Z would be equal to, R is 0.029 times cosine of theta is the power factor, so 0.8 plus, and there's no J here though, so be careful when you do this, 0.048 sine of theta, it would be sine of 36.6 for the power factor, that's 0.6, and this Z is equal to, what did I get, 0.052 ohm. But remember, this is per 1,000 feet, so we're gonna have to divide this by 1,000 feet and multiply by 250, which is our, right? So Z becomes 0.013. Right? So then we have our impedance here already calculated. We can calculate the voltage drop across that. So V is equal to IR. I is 400. R is 0.013. And we have 5.2 volt. And this is a line to neutral voltage. So we have to multiply this by, let me do this, V phase. So V line is then equal to this times square root of 3. And this becomes 9 volt, approximately 9 volt. So we have 480 volt for the source. We have a voltage drop of 9 volt. Therefore, the voltage here would be, let me use a different color. That's fine, I can use red. V is equal to 480 minus 9, which is essentially the same thing that we got before. So either method you use will get you to the result. All you need to do is just be really, really careful when you, especially when using the table 9. Because you see the first value and you automatically think that that's your R value. So I can see that happening. You can easily put 0.0048 plus J 029. It's going to mess up your entire calculation. So essentially what we did here, I don't have to repeat myself, but I feel like sometimes I have to. Two methods, right? You can calculate your Z, effective Z, and then straight apply V equals IR, get your voltage here and subtract your source voltage. Or you can just go ahead and straight and just recognizing that, you know, I mean, it's the same thing essentially, but I'm just doing everything under one calculation instead of going back and forth. So I like the first method personally, but you can use either way, especially here in the table. I mean, either method works, but if you notice here, sometimes when you're given a power factor of 0.85, the second method works better because you don't have to calculate the impedance. It's already given per the table. If you have a power factor of 0.85, it's already given. You just recognize it and use it straight, the impedance value. So if you were given a 0.85 power factor, this value here would just get that straight from the table. And then this 0.052 would be straight from the table. We don't have to calculate anything at all if we had a power factor of 0.85. And then you divide by feet if you're given feet, or kilometers if you're given kilometers. But typically it's per feet. So, you know, either way you do it, it's essentially the same thing. Don't forget that you are calculating the voltage here line to neutral, not line to line. So if you have any questions, let me know. If you have another method to solve this, let me know as well. I'll be here to answer your questions and here to help as well. Thank you.